In this part of the lecture, I want to dive a little bit into homogeneous coordinates. Homogeneous coordinates are a tool that we're using in photogrammetry, computer vision, and robotics very frequently because it allows us to do certain tasks much more elegantly compared to the Euclidean space. And therefore, it's an important mathematical toolbox that you can use in order to write down equations in a very compact fashion and, for example, perform transformation elegantly and also have possibilities to represent, for example, points or geometric objects which are infinitely far away with finite numbers. And that's something which is also an important thing and becomes very handy when we are performing state estimation problems or want to represent certain equations that involves points that are potentially far away. So why a projective space, what homogeneous coordinates are? The reason for that is that we often use cameras in our discipline, and cameras basically take the 3D world and project them onto a 2D image. So there's a popular pinhole camera model that you all know. So you have an object in the 3D world. So this is our object over here. And so you have, for example, light source like the sun. This is reflecting light towards the camera. The ray passes through that pinhole and generates an image on the image plane over here. Often, although this is kind of the real image plane, we're using a virtual image over here, which sits kind of in front of the camera. Although this doesn't exist in reality, it's sometimes easier to visualize things. It's basically this image plane rotated around the pinhole in front of the camera, so the object actually stands upside down. And what happens in this pinhole camera model, you have this small hole, which is infinitely small, and all the rays, all the light that reaches my image plane passes through this point. So it's basically a bundle of rays of light that reaches my image plane. And what happens over here is this light generates an image, and this image is a projection from the 3D world onto the 2D image plane. And it's a projection, as we say that. So it will, as we will see, is a projective space is can more elegantly describe this model, and therefore we are frequently using it because whenever projections are involved, certain things can be formulated simply in a more compact fashion, especially transformations, which makes this very, very attractive. So if we have an image, for example, such an image that we have generated here, the question is, what can we say about the geometry of the image? So for example, if we have certain lines, do parallel lines from the real world stay parallel in that image? Or do angles between lines change? So if we have in the 3D world two lines which have a certain angle with respect to each other, is this angle preserved in an image? And it turns out, for example, that this is not the case. So it's not an angle preserving mapping. But typically, straight lines stay straight lines, at least in the pinhole camera model. And there are certain properties of the geometric objects, how they are changed when I'm projecting them from the 3D world into an image. Just to mention a few things, so straight line preserving mapping means that straight lines are mapped into straight lines, and this is something that, at least if you don't have lens distortions, if you just have kind of the basic pinhole model, that's actually the case. So if you have a straight line in the real world, it stays a straight line in your image. It is not length preserving. That means you have two objects in the real world which have the same size, but they may be mapped to a different size in our image plane. For example, if one is further away from the pinhole camera than the other object, this leads to a different size in the object in the image space. And it's not an angle preserving mapping. That means the angle between two lines, for example, doesn't stay the same if you project them from the 3D world onto the 2D image plane. There's an example as we can see here. So these are two lines which are parallel in the real world. These are also two lines which are parallel in the real world. And we can see, and they have kind of a 90-degree corner over here. We can see that this is definitely not the case in the image. So just as an example that straight lines stay straight, but parallel lines may not remain parallel because the angle between lines can actually change. Another interesting thing is kind of the vanishing point. If we have parallel lines in our image, then we have a vanishing point and those lines move towards this vanishing point. So that means, again, parallel lines in the real world, which those tracks are at least approximatively, do not stay parallel in my image, right? So those lines are not parallel in my image plane. And the fact that those lines do not stay parallel is something that we want to actually encode in this projective mapping that we want to express. And these parallel lines we can describe as kind of meeting at infinity. So if we have parallel lines and we approach this towards infinity, then these are two lines which are actually intersecting, but the intersection point is infinitively far away. So you can see that if you have two lines which intersect in the Euclidean world, like my hands over here, and I'm increasing the angle, decreasing the angle between those two lines, the intersection point moves further and further and further away. And when they become parallel, this point moves infinitively far away. And so this is something that, as we will see, something that we can represent really elegantly with homogeneous coordinates, for example. And if you have parallel lines in our image, then every direction leads to one vanishing point, and exactly one vanishing point. So if you have parallel lines and we kind of move the train tracks, so to say, or we move our camera point of view so that they are at a different location with respect to my camera, they will generate actually a different vanishing point in the image, but every set of parallel lines has the same vanishing points. And so one of the questions that we have here, how can we describe these points which are infinitively far away in an elegant fashion? And it turns out that homogeneous coordinates are a very good tool for actually realizing this. It's important to say that the projective geometry that we are looking into is just a different way for representing our space. And it's motivated by the fact that certain things cannot be expressed that elegantly in the Euclidean space, in Euclidean geometry. And it's suboptimal, for example, for this central projection, so what happens in the pinhole camera model. And that doesn't mean we can't express it in general in the Euclidean space. The thing is that it becomes more complicated to write down the equations, and the equations don't become very handy, and the mathematical expression become complex. And therefore we can go to an alternative representation, and these are these homogeneous coordinates, which are better suited for describing. So homogeneous coordinates are a system of coordinates that are often used in projective geometry, and they make things simpler compared to the Euclidean space. And there are two important properties that we will especially exploit in here. The first thing is that they can elegantly represent points which are infinitively far away without using infinity as a number. So we can use finite numbers and still represent points which are infinitively far away. And that's something which becomes very attractive, as we will see. And the second thing is it's also a very good tool, and therefore it's also used outside problems where projections play a role. So even if you have a state estimation problem, for example, where projections are not involved, homogeneous coordinates can be very elegantly. And one of the reasons is that they can describe different transformations in a unified fashion with matrices. So a rotation can be described, for example, through a matrix vector multiplication. That's the same for the Euclidean space, but it also holds for translations. And that's something that the Euclidean space, for example, cannot do. So the last two bullet points here are the things why we are using it here as an attractive tool for our state estimation problems. So before we start, a few words about the notation. So if we have geometric objects such as points, lines, or planes, they're typically described with this capital calligraphic fonts. So, for example, X, Y, or P typically represents a point and describes the geometric object point. And we can express this in different coordinates, either in homogeneous coordinates or in Euclidean coordinates. And for that, we'll be using different fonts. So if you see this type of fonts, we are talking here about homogeneous coordinates. If we use this type of font, we are talking about something represented in the Euclidean world. L or M typically refers to lines and A to planes. And another thing which should make your life easier, everything which is lowercase means we are referring here to the 2D world. So for example, 2D Euclidean world, if we move on a plane or live in a plane. Or if it's a capitalized character, then it means we are in the 3D world. So just by looking to the variable on the slide, you can actually see if we're talking about 3D or 2D. Or sometimes if we're talking general, I may also use lowercase, but otherwise it means that we are living in the 2D world. Okay, so let's start and look into homogeneous coordinates. What is this and what's a homogeneous object? So the representation of a geometric object is something that we call homogeneous. And what needs to be done for this is if x and lambda times x, where lambda is a scalar unequal to 0, represent the same object. That means x equals 2 times x, for example, or x equals 3 times x, or x equals 0.5 times x. So this refers to the same geometric object, then it's something which is homogeneous. So we can write this down. So this equation holds. We have a vector, this vector x is the identical vector, and this is lambda, and this lambda must be unequal to 0. So for 0 it doesn't hold. But for every number unequal to 0, this equation holds. And this is clearly something that doesn't hold for the Euclidean space. So in the Euclidean space, this is not the case. This would only hold if lambda would equal to 1. So we are more general here. So those two things represent the same object. Okay? So that's the definition what a homogeneous object is. So something that is defined only up to a scale factor. So now let's become a little bit more concrete. How does this look like, for example, for a point in 2D? So if you have a 2D point in our 2D Euclidean world, point x with an x and a y coordinate over here. So boldface is a vector, and these are the individual coordinates in regular characters. So then, to go to Euclidean coordinates, we turn from an n-dimensional space to an n+1 dimensional space. That means we add one additional dimension, and this is the last dimension that we add here to our vector. So a 2D vector turns into a 3D vector. A 3D vector turns into a 4D vector. A 4D vector turns into a 5D vector. And the last dimension in this vector is set to 1. So if we move from our Euclidean world to our homogeneous world, to our projective space, we add a 1 as a last dimension. And that's basically it. There's nothing else that we do for representing a point or transforming a point from our Euclidean world into our homogeneous world. And this is then from R2 into the projective space P2. So it's our two-dimensional projective space. Okay, so that means if we say that a point is homogeneous, is only defined up to a scale factor, that means if we take our Euclidean point xy, turn it into a homogeneous vector xy1, that means we can multiply this point x with an arbitrary weight, for example, w unequal to 0. That means all three coordinates need to be multiplied with w. So w times x, w times y, w times 1 is w. So it turns into a point u, y, w, where u equals y, w times x, and v equals w times y. Okay? So, and this is the same thing. So what we have written over here, x, y, 1 is the same as u, v, w. This is comes from the homogeneous property. And then the constraint that we have, a point x in the 2D plane is represented by a three-dimensional vector. This is my u, v, w. And the constraint that I have is that the squared norm of this point, so u squared plus v squared plus w squared, must be unequal to 0. So that means not all three coordinates can be 0. Okay, so if I have a point in the homogeneous coordinates, it's not allowed that we have the point 0, 0, 0. All right? And as we said that the point is only defined up to a scale factor, and if we want to turn this point back to the Euclidean world where we need to get rid of the scale factor again, that means we normalize by the last coordinate. That means if we have this three-dimensional vector, we take the first two coordinates, copy it over, and divide both of them by w. So if I want to go back to my Euclidean coordinates, the first coordinate gets u divided by w, and the second one v divided by w, where again w must be unequal to 0. So this then turns into u divided by w, which, if you remember, u was x times w, so if x times w divided by w is equal to x. So I get back my original point in my Euclidean world, and even if I'm in the homogeneous world, scaled it with an arbitrary factor, through this division by the last coordinate, I'm taking this scale factor out again, returning back to our Euclidean world. So just as a thought experiment, what would actually happen if my term w, my weight, my last dimension, would be 0? Just assume it's 0. If it is 0, that would mean, if you turn it back into a Euclidean point, so something that we can actually better visualize in our brains because we're used to that, that would mean we would take a value u and v and would divide it by 0. And that would mean those points would take arbitrarily large values for x and y, or let's say if y would be 0, then only the x coordinate, for example, would be infinitively large. So it leads to values which are infinitively large as the coordinates of the points. And that means this is a point which is infinitively far away. Okay, so if the last coordinate is 0, that means we have a point which is infinitively far away. And this can, in the Euclidean world, only be expressed through an infinitively large number. So infinity basically is the x, y, or x and y coordinate. And this is equivalent to a point that is, has a weight of 0. So just an example, the projective plane, these are kind of all the points in P2. They contain all points that we know from our Euclidean world. So if the point has an arbitrary point xy, we add the point xy1, so there's an element of this projective plane. So all the points from the Euclidean world sit in this plane. What we don't have in that plane, however, what we additionally have in that plane are all points which take a 0 in the end. So a point that I cannot generate directly out of an Euclidean coordinate, because if I come from the Euclidean coordinate, I have this weight vector of 1 over here, and these are the points which are infinitively far away. So if the last coordinate is 0, then it's a point which is infinitively far away, and the first two coordinates here just basically specify the direction where that point is in the world. And the only point which is not part of that projective plane is the point 0, 0, 0. This is explicitly taken out, so the 0 vector, where all dimensions are 0, is not part of P2. So if you want to go from homogeneous coordinates back to the Euclidean coordinates, we can write this as u v w, so my arbitrary vector, only w, my arbitrary vector. So this is equivalent to u divided by w, v divided by w. So I'm taking these two coordinates divided by the last coordinate, so that this turns into 1. And then I'm basically dropping the last coordinate, because if this is 1, I can go from homogeneous coordinates to Euclidean coordinates by dropping the last dimension, and then this is equal to my point x and y. So let's try to visualize this fact again. So what you see here is a three-dimensional space, and this is the three coordinates that we have in our Euclidean world. What you can see in here is there's a plane where the z coordinate equals to 1. This is this gray plane over here. And if the z coordinate, or let's call it the third coordinate, not the z coordinate, but the third coordinate equals to 1, that means the other two coordinates represent the point in the Euclidean space. And so this gray plane here represents the Euclidean space, the Euclidean 2D Euclidean space. We, however, have a vector with three values. The first two values sit in here, and the third value is 1. Then we end this gray plane. But we can also be outside this gray plane, right? So we can be anywhere in this three-value, three-dimensional space. And so any point that has, where I, for example, multiply the xy coordinate with, let's say, 2, I get 2 times x, 2 times y, and the third coordinate would be 2, would be a point which is sitting higher up here, so on third coordinate equals to 2, and every point which lies on that line towards 0, 0, 0 represents the same point in the Euclidean world. So we can see that all points which lie on that black line in this Euclidean space represent this single same point in my Euclidean world. Okay? And only this plane down here, these are the points which are infinitively far away and which then cannot be represented with the Euclidean coordinate or in the Euclidean space, because this is a plane which sits up here. Okay, what we can do in 2D, we can also do in the same way in 3D. So the analogous thing to 3D, from 2D to 3D is we have a 3-dimensional vector and we turn into a 4-dimensional vector, right? We add this 1 dimension and add 1 to it. Exactly the same thing. And also the way back is very similar, that we take all the coordinates that we have, in this case 3 and not 2, and divide it by the last, in this case 4th coordinate. So if you have u, v, w, t, and t is now our last dimension, that means if we want to go back from homogeneous coordinates into Euclidean coordinates, we first divide the vector by t, so we're still in Euclidean space, where you can u divided by t, v divided by t, w divided by t, and this turns into 1. And as soon as I have a 1 sitting over here, I can drop this dimension, and then it brings me back to the Euclidean space. Okay? So what we can do in 2D, we can do exactly the same way in our 3D world, representing a point in P3, from R3 to P3 in this example. And then the origin of the Euclidean coordinate system, this may be set because this may lead to some confusion, is the point 0, 0, and the last coordinate is 1, or 0, 0, 0, 1. So this is the origin in the Euclidean world. Remember, the point 0, 0 is the origin in R2, and this is the plane R2, so it's exactly this point over here. So that means the origin of the Euclidean coordinate system in homogeneous coordinates is the 0 vector where the last dimension is still 1. It's not 0, 0, 0. This would not be part of that space. So it's kind of the important thing that you need to keep in mind. The origin is 0, 0, 1 or 0, 0, 0, 1 in the expressed in homogeneous coordinates. So the next thing I want to look into are transformations. And this is one thing which is the reason why homogeneous coordinates are so frequently used, because you can write down change of transformations in a very, very easy way. And so the transformation can be expressed through a matrix vector multiplication. So again, X is my an arbitrary homogeneous object. Those examples here will be done in 2D or in 3D now. And I can perform a projective transformation by multiplying a matrix H, in this example, and then the vector from the right-hand side to this matrix H. And we're talking here about an invertible mapping. So projective transformation is an invertible mapping of that form that takes a point x, you multiply h times x, and it gives me a new point x prime. And let's have a look how this matrix H actually looks like, and try to make the connections between the Euclidean space. So what is a translation in the Euclidean space, in the 3 Euclidean space, for example, and would be a translation by x, y, and z. So I have a shift in x, shift in y, and shift in z coordinate. Can be expressed by a matrix H. Again, the matrix H is a homogeneous object, so it can be multiplied with any arbitrary scalar factor. This was our homogeneous property. And then I have this matrix H is a 4x4 matrix, because we're representing the 3D Euclidean world. And this identity over here is a 3x3 identity matrix. So this matrix over here, a 3x3 matrix with 1 on the main diagonal and 0 everywhere else. This is a 3-dimensional vector 0, so 0, 0, 0. This is a scalar 1, and this is a vector t, a 3-dimensional translation vector. And this vector t represents the shift in the x, y, and z coordinate in our Euclidean world. So if I use this matrix over here, so it's a matrix which has basically a 4x4 identity matrix, so it's 1 on the main diagonals, except that the last 3 values over here contain the translation vector tx, ty, tz. And if I then multiply a point on the left-hand side to this matrix H, it's equivalent to shifting the point, translating the point in our three-dimensional world. And this is an elegant thing because that's something that I cannot express in Euclidean coordinates through a vector, matrix vector multiplication. I only can do this by adding a vector to it. And if we can express all the transformations as matrix vector multiplications, this becomes very elegantly because they can simply chain those by multiplying those matrices together, for example. Okay, so but this was only a translation. Let's see how that looks like for more complex transformations. What about a rigid body transformation? A rigid body transformation is a transformation which has three more parameters, so a rotation and a translation. So let's look to the translation maybe first. How can we express rotation in this Euclidean space? It turns out I take the same H matrix, and this identity matrix over here, I put in a regular rotation matrix as you know them from our Euclidean world. And of course, if I only want to rotate something, there's no translation involved, so this three-dimensional vector must be the zero vector because there's no translation involved. So I basically have a matrix which has the last column and last row are 0 except the last element and the last element down here, which is 1. And over here, I have a 3 by 3 space which is left, which is filled with a regular rotation matrix. Just as a reminder, rotation matrix is something we discussed in the previous lecture. This is how the standard rotation matrix looks like in a two-dimensional space and how different rotation matrices around the x, y, and z coordinate look in the three-dimensional space. And we can just multiply, for example, 3 rotation matrices together or even more than that and obtain an arbitrary rotation in the 3D world. And this is the rotation matrix which sits there in this rotation here. So this R is exactly this rotation matrix. And this allows us to express a rotation of rotating a point in homogeneous coordinates through this transformation into a new point. And if we turn that back into the Euclidean coordinates, we get exactly what we would get if we would execute a rotation in the Euclidean space as well. So other important transformations are rigid body transformations. So rigid body transformation consists of a rotation and a translation. And it's then 6 parameters, 3 for the translation part and 3 for the rotation part. And this is now expressed in that way. So it contains of basically the rotation transformation and the translation transformation. I have my R sitting over here, my rotation matrix, my translation over here, a 0 vector and a 1, and everything is only defined again up to this magic scalar factor. And this is, if I multiply now a point with this transformation H, it basically executes a rigid body transformation consisting of a rotation and a shift and a translation. And this is exactly what it has. So if you multiply a point here from the left-hand side, the point will be rotated by the rotation matrix R and translated by the vector T. Okay, now let's look into other transformations. They're more than just translation, rotation, and rigid body transformation. So there's, for example, the similarity transform, which is a very frequently used transformation in computer vision or in photogrammetry. This basically adds an additional parameter, a scale factor. And this is a scale factor which scales the points down. So, and here we cannot just, in the Euclidean space, multiply the whole transformation with a scalar because this is the homogeneous property. That wouldn't change the object itself. So we only need to multiply this rotation matrix here with a scalar. So we are basically not scaling this, the 1 down here. And as a result of this, it will just make our objects larger or smaller. So this small m is the scaling factor that we know how we would scale in our Euclidean space. So this is, again, still an angle-preserving mapping because we are just rotating something, we are shifting something, and we're making things larger or smaller in the same way in all dimensions. So all angles stay the same under this similarity transformation. If we now go to an affine transformation, which has additionally 3 shear parameters involved, and maybe even scale parameters in x, y, and z differently, then we end up having 12 parameters. So 3 translations, 3 rotations, 3 scale parameters, and 3 shear parameters. And then we still have these zeros down here, our translation vector here, our 1 sitting down here, but this matrix, which was a scaled rotation matrix before, turns into an arbitrary matrix because we have 3 degrees of freedom sitting in here, so we have 9 degrees of freedom sitting in here. So 3 from rotation, 3 from scale, and 3 from shear. So this is now an arbitrary matrix A, which has 9 elements and 9 degrees of freedom. And this we can use to express an affine transformation. So an affine transformation means that parallel lines still remain parallel, but it's not an angle preserving mapping. So angles between lines, for example, in this world will change. And then we can go even further to a projective mapping, and the only 3 parameters we still have actually sits down here. So what happens if we have this, add the 3 degrees of freedom in here? If we add the additional 3 parameters here into a vector, this turns then into a projective transformation. And this projective transformation has 15 degrees of freedom. Again, this is a 4x4 matrix, so it means 16 values, but this one is 1, so we have 15 degrees of freedom. And these are the reasons why parallel lines may not stay parallel. So if you have a projective transformation, which goes beyond or extends the affine transformation, we get 3 additional values over here, and as a result of this, parallel lines may not stay parallel. Okay, so what we have seen now is that we can express projective transformations, affine transformations, similarity transformations, rigid body transformations, rotations and translations and scaling very elegantly through the same object, through a 4x4 matrix for the 3-dimensional space. And this allows us to chain those matrices simply by matrix multiplications next to each other. Just for illustration purposes, what this slide shows the different transformations for 2D that we can do, from transformation, mirroring, axis rotation, motion, similarity transform, scale differences, and so on and so forth until the projectivity. And you see the degrees of freedom and how this matrices actually looks like. So which parameters are fixed, which type of value, and what I've discussed here are basically the representation of this matrix H. This is what we have done for 3D now, and here's a nice overview for 2D. So in sum, we have this hierarchy of transformation. The most general one is this projective transformation, where parallel lines may not stay parallel anymore due to the projection. The affine transformations, which is not angle preserving, so angles may change, but parallel lines stay parallel. The similarity transform, which is an angle preserving mapping, so angles stay the same, just the size of the object may change. The rigid body transformation doesn't scale the object, it keeps its size, and this can be then split up into a translation and rotation. And you also see the number of free parameters for 2D and 3D in this plot. By expressing those transformations as matrices, as I said before, we can very easily chain those transformations, something we see down here. So if we have 2 transformations, H1 and H2, and we want to execute H2 and then H1, we can express this by H1 times H2 times X. And so X is first transformed through H2 and then transformed through H1, and then gives me my point H prime. I could also multiply those 2 matrices together because they're just 4x4 matrices, so I can multiply them with each other. We'll get a new 4x4 matrix, which expresses the combinations, the chaining of these 2 transformations. But as a note, this is not a cumulative operation, so executing H1 and then H2 is different from executing H2 and then H1. You may remember this from the rotations through this, because in general, matrix multiplication is not commutative. So that's something that you also have to take into account here. But the other thing, which is also elegant, that I can easily invert a transformation. And inverting a transformation can be obtained by just inverting my matrix H. So if I have a point X, which is transformed through H into X prime, what I can do is I can take this matrix H, compute its inverse, multiply H prime from its right-hand side, and then we'll actually obtain the original point X. So I can use these transformations as matrices as I'm used to be. I can chain them, multiply them, I can invert them to invert the transformation. And that is something that I can also do in this homogeneous coordinates, and which allows me to very elegantly combine and invert different transformations with which points are executed in the real world. And this is important if you, for example, you have a camera which is moving through the environment. You want to describe the motion of the camera with translations, with rotations, or a mobile robot, for example, or you have a scene and you want to shift and rotate the scene and scale the scene, then it's a similarity transform, or you have points in the 3D world which are projected onto a camera image, then all these things, these transformations, are very, very useful. And therefore, they're such a frequently used tool in photogrammetry. So to go a step further, what else can we do? What is also important in here is, and what I want to dive a little bit further is into other geometric objects, especially looking into lines. We can also see how we can represent those lines in homogeneous coordinates, and that we can do attractive manipulations with those homogeneous representations of the lines that allows us to do certain operations like checking if a point lies on a line, or if computing the intersection between two lines in a very easy and elegant way. So let's have a look how we can actually represent lines in homogeneous coordinates. So we can have different ways for representing lines, how we do this in the Euclidean world. Depending where you went to school, you have seen different ways for doing this. The first prominent example is the so-called Hesse normal form. There we have an angle which represents the direction of the line and a distance d from the origin, and we can express this line with the equation x times cosine of the orientation of the line plus y times the sine of the orientation of the line minus the distance d to the origin should be equal to 0. Or you can go for this intercept form, which is shown here, or most prominently the standard form ax plus by plus c equals to 0. And this is all called the implizite form in German, or the standard form, which is a common way for describing a line through this form of equation. Okay, so what we can see in here is that we typically have 3 parameters to represent a line. This can be the 3 coefficient of the standard form, or 2 quantities that depends on the angle of the line, and 1 that depends on the distance of the line to the origin. And now we can take those 3 values and arrange them in form of a vector. And before we do this, we want to kind of rewrite those equations a little bit so that all kind of have the same form. So we are rearranging these 3 forms such that we always have an equation where the first parameter is a coefficient times x, the second term is another coefficient times y, and then we have a constant and equals to 0. So it's a very easy way if we can trivially rewrite Hesse form, intercept form, and standard form so that they fulfill this equation, as you can see it here on the right-hand side of that slide. So if we have that, we can always see that we have coefficients that sit in front of x, coefficient that sit in front of y, and a constant part, and then equals to 0. So what we now want to do is we can take these coefficients and arrange the coefficients in form of lines. So these are always equations that are equal to 0, and we take out the coefficients of these equations and put them in a vector form. And this is then our representation of a line in homogeneous coordinates. So again, we can do this in 3 different ways. If we take the standard form, it would be a vector with the coefficients a, b, and c. If you prefer the Hesse form, this would be the cosine of the orientation of the line, the sine of the orientation of the line, and the negative distance to the origin, or the corresponding elements in the intercept form. And if we then have a point and want to see if a point lies on a line, so if a point fulfills the equation, we basically need to check if a times x plus b times y plus c equals to 0, right? Because this is the equation that a point that lies on line must fulfill. So what we can do is we can take one of those 3 forms over here, it doesn't matter which one, and multiply it with a point, x, y, 1. And if this equals to 0, then we know this point lies on a line. So that is actually very conveniently written as x multiplied with the line equation must equal to 0. So through the dot product, we can express the fact or the test if a point lies on a line. So if we multiply a line, given with all 3 parameters, with a point x, y, 1, and the result is 0, it means the point lies on that line, because that means that it fulfills the line equation. So just by using dot product, we can very elegantly check if a point lies on a line. So more formally, we can define a line in homogeneous coordinates in 2D as a vector containing of 3 elements, L1, L2, and L3. And the important thing is that not all quantities can be 0, so at least one of those quantities must be unequal to 0. And then this three-dimensional vector represents a line that corresponds to a line in the Euclidean world that fulfills this equation which is shown down here. So it's basically the standard form where the 3 dimensions of the line vector are the coefficients of the standard equation used for a line. Okay, so it's the only thing we do, we basically take the 3 parameters that the line has and arrange it in vector form, and not all quantities are allowed to be 0. And then, if you want to test if a point x lies on a line L, the only thing we need to do, we need to compute the dot product x times L, and must check if it's 0, yes or no. If it's 0, the point lies on a line. If it is unequal to 0, the point does not lie on a line. So it's a very easy to execute test that we can do. Okay, we can go further and see what happens if you actually want to compute the intersection of 2 lines. So given that we don't have a point in the line, but 2 lines, and we want to compute the intersection of those 2 lines, can we do this in an efficient manner? And as it will turn out, we can actually do this in homogeneous coordinates in an efficient way. So what needs to be done so that we can compute the intersection of 2 lines? So again, that means we want to find a point, x, which lies on both lines, because then this is the intersection of the 2 lines. That means we can, if we have a line L and a line M, we can set up 2 equations saying first x times L must be 0 and x times M must be 0. These are 2 equations that need to be fulfilled. And so that's something we can very easily arrange in a system of 2 linear equations with 2 unknowns. So L times x must be 0 and M times x must be 0, and we can arrange it in this form. And we can, if we expand this expression, we can also express it in the following way by moving the constant part here to the right-hand side of this equation. So then we have a 2 by 2 matrix multiplied with a 2-dimensional vector, and our equals another vector, and this is kind of the standard way for representing a system of linear equation here with 2 unknowns and 2 equations. So how do we solve this? We can take an arbitrary technique that we have in order to solve this. One of the easiest way to do this here for this 2 by 2 system is to use Cramer's rule. So as a short reminder, if you want to solve a linear system, ax equals to b, you can compute this by the different dimensions of x are, so x1 is the determinant of the matrix A, where we replace the first column of A with the vector B divided by the determinant of A. And if you want to compute the second dimension of x, this would be then taking the matrix A and replacing the second column of this matrix A by the vector B. And the only thing I need to do, I need to compute these 2 determinants and divide them through each other, and this gives me the result for x. And this is especially something which can be very easily done in 2D, because in 2D the determinant can be very easily directly computed without needing to do a lot of complex instructions. So let's go through that step by step. I want to compute the solution of that system that is shown here, which is the system I need to solve in order to find the point at which 2 lines L and M intersect. So by just the straightforward application of Cramer's rule, I know that the x-coordinate of the intersection point is d1 divided by d3, and for the y-coordinate d2 divided by d3, where d1, d2, and d3 are the 3 determinants. One for this, the first one, the matrix A where the first column is replaced, d2, the matrix A where the second column is replaced, and d3 is the original determinant of the matrix, or the determinant of the original matrix A. Okay, and these are the ways we can compute the determinant. Again, if you want to compute the determinant of this matrix, for example, it's L1 times M2 minus M1 times L2. And if you expand this, you get exactly those expressions down here. Okay, so this is my result, and now what I'm doing, I'm just taking this fact or this result over here, and I'm just slightly rearranging this. So this is a copy-paste, the solution of Cramer's rule, and then I can rewrite this in homogeneous coordinates by saying my solution x is a vector x, y, 1, which is the intersection in Euclidean coordinates, and this is nothing else just from the result of Cramer's rule as d1 divided by d3, d2 divided by d3. And now I can write this in homogeneous coordinates as d1, d2, d3 as a vector with 3 components. And if I would take this vector and go back to the Euclidean world, you know, I have to divide by the last component, so I exactly get this result, and then I have my point in my Euclidean world. So this means I can obtain the solution by writing it in homogeneous coordinates as a vector d1, d2, d3, where these are the 3 different determinants computed based on Cramer's rule. Okay, if you now carefully look to this vector d1, d2, d3 with those elements in here, this is actually the result that you obtain if you compute the cross product of 2 vectors in 3D. So the result that we have for this system can be expressed by this vector x, exactly in the way we did it before, and I can actually take out this d3 just to see the correspondences to the Euclidean world, and then this is nothing else than L cross product M. So by computing the cross product of 2 lines, I actually obtain the point, the intersection point of those 2 lines. That's an interesting thing. It just kind of lets you write down the intersection of 2 lines in a very elegant way just by L cross X. And so you can, if you have a mathematical equation where you need to compute the intersection of 2 lines and then continue working with these 2 lines, you can write it down in this very elegant way. So it makes the mathematical notation much, much more compact, and is very elegant if you write things down in homogeneous coordinates. So just to summarize this, we said to test if a point lies on a line with the dot product of the point and the line, and it must be 0. And if we want to compute the intersection of 2 lines, we obtain the point x as the intersecting points of L and M just by computing L cross M. So it's a very simple and elegant way for computing the intersection of 2 lines using homogeneous coordinates. So then we have one operation more, which we commonly use. We have 2 points, and we actually want to fit a line through those 2 points, or compute the line parameter that generates a line that goes exactly to those 2 points. And this is again something we can do in a very elegant way. So homogeneous coordinates also provide us with a simple way for computing the line that goes to 2 points. So now consider we have 2 points, a point x and a point y. So xi are the 3 parameters in homogeneous coordinates of the point x, and y the corresponding one. And our line L has the parameters L1, L2, and L3. And now the question is, how can we find the line that connects those 2 points? So how to determine L so that L passes through the points x and y? And we can formulate this again in a very similar way by saying the point x must lie on L and the point y must lie on L. So I can again write L dot x must be 0 and L dot y must be 0. So 2 things I exploit, that both points must lie on the resulting line that I want to compute. So basically it turns out into a system which is more or less the same to what we had before when we computed the intersection of two lines, except that now we want to obtain the point, we obtain the line given 2 points, and before we want to obtain the point given that we had 2 lines. But in the end, both are 3-dimensional vectors, nothing else than that. So it turns out that I can do more or less the same steps that I did before and compute, solve this linear system using Cramer's rule, and then come up with my result. The only difference was before, these were here just kind of 1 parameters and not 2 parameters involved, so this requires a very minor modification, but the result in the end will be the same. So we can use Cramer's rule to solve this linear system over here, and again, as it was done before, the first and second solution of the line parameter is given by d1 divided by d3 and d2 divided by d3, and then written down exactly in the same way. So it's directly the application of Cramer's rule as we used it 5 minutes ago for computing the point that intersects two lines. Okay, so then I can, if I get again my vector d1, d2, d3, I have my parameters L1 and L2, and now I can use, define a third line parameter, which is my L3, and then I can say this is L3 equals L3 times d3 divided by d3, and then I use this for a small trick, because then I can write my line equation in this form: d1 divided by d3, d2 divided by d3, d3 divided by d3 times L3. So I can move L3 divided by d2 out of that equation, and I do this in order to simplify these terms d1 and d2 here, so that they turn into the result that corresponds to the first two dimensions of the cross product. So this is just kind of moving an expression out of the vector, so that this turns into a cross product. And as we have a homogeneous object, as long as this expression is unequal to 0, and this is the case because otherwise the determinant of our system would be 0, and as this is not the case, this expression is unequal to 0. And so this is just the constant scaling factor that we know from homogeneous coordinates. So we can simply drop this vector over here because we have a homogeneous object and still identically the same. And as a result of this, this expression equals to this expression because I can drop this scaling factor. So my line parameters L turns into nothing else than x cross y. So in order to compute the line that goes through 2 points, I just need to compute the cross product of the 2 points. So x cross y gives me the line. So to summarize these 3 properties that we have derived now, to check if a point lies on a line, we just have to compute the dot product of the point and the line, or the line and the point, because of course it's commutative, the first operation. And for computing the intersection of 2 lines, the intersecting point is the cross product by the 2 lines, or computing a line that passes through the 2 points x and y is again computed by the cross product. So very simple operations that we can use later on if we have lines in our image and we want to do operations with those lines, having a line, putting through the points, computing the intersection with something else. These mathematical expressions become very handy because they simply allow us to write things in a very compact way. And therefore, this is something that we will also use later on in your studies, or you will have to use in your studies when we operate with images and lines and images. The last point I want to look into are points and lines in infinity. So I said before in the lecture that one of the elegant things of homogeneous coordinates is that we can express geometric objects which are infinitively far away, like a point at infinity. And we can actually do something similar with lines. And what I want to do now in the next minutes, elaborate that a bit further and dive into the details of what it means to have a point or lines at infinity. So we have seen before that the last component of this homogeneous vector is important, and if it is 0, the last dimension, so like in this case over here, this is an element which cannot be represented in Euclidean coordinates, at least with finite values for the other dimensions. So this was kind of the z equals to 0 plane in this visualization that I had before, the third component. It's not actually the z component, but the third component. And this was kind of a plane which was parallel to the Euclidean R2 plane in this illustration. And these were the points which lie infinitively far away. So what we have, if we have a point which is infinitively far away, we sometimes want to make it explicit, we write this infinity down here, which means nothing else that the last component is 0 and the other 2 components are still here, and these are finite coordinates. So remember, the important thing is we have a vector which only contains of finite numbers, but it represents a point which is infinitively far away. And the interesting thing, or the important thing that we have in here is that we maintain the direction where that point is. And those first 2 parameters indicate that the direction of that point. You can see this if you think about the Hesse form, because the first two parameters from the Hesse form was the cosine and sine of the orientation of the line. So it tells me in which direction I'm actually looking to. And the last point was just related to the distance to the origin. So this is a great tool when you work, for example, with cameras. You know, if you have a camera and you make a picture of an object, you do not know how far that object is away. You just know the direction of the object. So you know in which pixel coordinate the object lies to, but you have no idea how far that is away. The point lies somewhere on the line, or the object lies somewhere on the ray of light, but can be infinitively far away. And the homogeneous coordinates are especially a great tool if you work with cameras to represent those facts that points can be infinitively far away, but we still know the direction. We can express the direction with finite coordinates. So if you consider you have a point which is infinitively far away, so wherever you are, you observe this point in the same direction. That's a very great tool in order to determine your orientation, so where you're looking to. Because if you know that in a certain direction, you always see the same object, like the North Star. The North Star is always in the same direction, there's north, no matter where you exactly are. This is a great tool for fixing the orientation of a camera or a robot moving through the environment. And the nice thing is you can explicitly express this with homogeneous coordinates. So let's have a look to all the lines which actually go to a point which is infinitively far away. The next thing that I want to look into, kind of check which lines actually intersect at that point which is infinitively far away. In order to do this, we can use the tools that we just derived by having checking if a point lies on a line. So we say we are interested in all lines L that intersect with this point x infinity. Again, x infinity was uv0. Okay, so uv0, and I'm interested in the line, or in all the lines which intersect with this point. So if a point which is infinitively far away, the question is now which lines intersect actually at that point which is infinitively far away. Okay, so if we now interpret the lines in Hesse form, we have seen that the first two parameters of those lines tell me the orientation to the line. So what's the heading of the line? What's the direction? Where is this line going to? And what this equation actually tells me, given that I know that the last coordinate of this vector of this point x infinity is 0, the third parameter of this line doesn't really matter because we'll anyway be set to 0. So the only parameters in L which I need to fix in order to make the lines intersect with that point are the first two coordinates. And these are exactly the cosine and the sine. So that means that u times cosine of the orientation of the line plus v times the sine of the orientation of the line must be 0. And this is a constraint that I have. The third component of the line doesn't matter. Okay, so that means that for all the lines which have the form, the first two dimensions are fixed through the orientation of the line, and the third one is indicated with the star, is kind of the free parameter. I don't care how far the line is away from the origin. All those points will pass through x infinity. And this equation over here, fixing the first two coordinates but leaving the last coordinate open, are basically all the lines which look into the same direction. So these are parallel lines. So that means all lines which are parallel will intersect at the same point in infinity. So all parallel lines meet at one single point at infinity. And that's kind of an important thing that we can exploit and take into account. That if we have parallel lines, those parallel lines will intersect in one single point which is infinitively far away from us. We can also see this in a different way if we look into exploit the fact that we want to compute the intersection of two lines. So let's design two lines and compute the intersection of the two lines. There's something that we can do with a cross product, as we have seen just a couple of minutes ago. So what we can do is we can say, okay, we have a line A, B, C, and we have a second line A, B, D. So again, the first two dimensions are identical, but the last two dimensions can be different. So these are two lines which are parallel. I don't specify the direction in which they go to, because I don't tell you how A and B looks like, but I can tell you that they are the same, so the lines must be parallel. So it's two arbitrary but parallel lines. If I compute the cross product between the two elements over here, then the important thing is that we can see is that the third dimension here is AB minus AB, because it results from having these two operations, combining these two dimensions. So this means whatever I do, the last component is 0. That means the point is infinitively far away. And the first two dimensions of this point only depend on the line parameters. Okay, so if I have two parallel lines, which I expressed over here, they meet at a point at infinity. And the line parameters, which I have in here, tell me which point that actually is. So all parallel lines meet at one point at infinity. And it's kind of a nice illustration here of the two lines, and they meet at infinity, just kind of as an illustration or a reminder for yourself for that fact. So those images always help you to remind those things in a nice way. So we can then look into infinitively distant objects. So we said an infinitely distant point is a point UV0. That is kind of the point which is infinitively far away. We can also look into an infinitely distant line, which is called the ideal line. And the ideal line has the parameters 0, 0, 1 over here. And as we will see in a second, this line, L infinity, can be represented as kind of as a horizon line, because it is a line which contains all points which are infinitively far away. So a line at infinity is a line that passes through all the points which are infinitively far away. You can have a line that passes through one point which is infinitively far away, and maybe your camera or the projection center of your camera. I'm not talking about this line over here. I'm talking about the line that passes through all points which are infinitively far away. And this is this line. How can we test that? We take all points which are infinitively far away, which are represented in this way, and compute the dot product with this line, which connects all the points which are infinitively far away, because all those points must lie on a line. So the product of x infinity and L infinity must be 0. So if I compute the product of x infinity and L infinity, it turns out that the first two components, as x infinity can take arbitrary values over here, must be 0 for that line. And as this value is 0 for x infinity, this must be a non-zero value for the line. Okay? And we can just write a 1 in here because it's only defined up to a scaling factor. So this must be 0. That means nothing else that this is a line, the ideal line, which connects all points which are infinitively far away. And kind of, you can visualize this kind of the horizon line. It's basically the whole horizon which spans infinitively far away. And that connects all points that are infinitively far away from you. So we can explicitly represent a line containing all the points which are infinitively far away from us. So this is something that we have done in 2D so far. We can do things in a similar way in 3D. So if we have a point in 3D, again, we have just a 4-dimensional vector to express the 3-dimensional point in homogeneous coordinates. And we can do a very similar thing for a plane and say a plane has simply can be expressed as an equation that equals to 0 with 4 coefficients rather than 3 coefficients, because now I have not only the x and y coordinate, I have x, y, z, and my constant. So I have 1 parameter more for representing my line. So, and I can do a very similar thing to check if a point lies on a plane in 3D now, again, using the dot product. So a dot x, where a is the plane equation and x is the point, must be 0, which can be expressed as a transpose x, or x transpose a must be 0. And though this is done in a very similar way, that I can use the standard equation of the line, saying A, B, C, D are the line equations, are the coefficients of my, plane equation. So A, B, C, and D are the coefficients of the plane, not line equation. Or I can express this also with a product of the normal vector and then the constants vector. There's kind of two different ways how I can actually represent this. And then I can also have, in a very similar way, points which are infinitively far away in 3D, which are points where the first three parameters are take arbitrary values and the last parameter is 0. And again, these are points in infinity, but now in 3D, not in 2D. But again, the first three dimensions are finite, and they determine the direction of that point. Just in 3D, we have one dimension more. In a very similar way, I can define this plane which goes through all points which are infinitively far away, and you can basically envision this as the sky. So it's kind of all points which are infinitively far away lie on this special plane, and this is the plane with the parameters 0, 0, 0, and then a constant value which is only defined up to a scaling factor. So we can do very similar things, what I've showed in 2D, also in 3D, and can exploit similar effects in here. So this brings me towards the end of the lecture today, which was a kind of introduction into the key things or key aspects of homogeneous coordinates that we will use here in the lecture. So there are a lot more things that you can do in homogeneous coordinates. It can also get substantially more complicated, especially also if you take into uncertainties into account and things like this. It's not always trivial, but homogeneous coordinates are a very, very useful tool. And the important thing to note, it's just an alternative representation for geometric objects and an alternative to the Euclidean representation that you are used to. Why are we using this? Because it allows us to do certain things in a more elegant way. So certain mathematical operations can be expressed easier if we operate in homogeneous coordinates. So we have seen this with, for example, chaining transformations or inverting transformations, which can be done very elegantly and dramatically simplifies the mathematical operations that you have. So especially if you think about a point from the 3D world which is mapped into a camera image, you have several coordinate systems involved. Where is the camera in the world? How are the internal mappings in our camera? How are the projections done? Maybe lens distortions come in later on. And for a lot of those operations that we do, we can actually write them down in these transformations in homogeneous coordinates. And then these are just simple matrix multiplications. So the math gets much easier if you use homogeneous coordinates in a lot of cases. The other interesting thing is that the homogeneous coordinates can represent points at infinity explicitly, so we can recover or maintain the direction in which that point lies, even though the point is infinitively far away. And there's also something that becomes very useful for bearing-only sensors, so cameras or sensors which only measures directions, such as regular cameras. And homogeneous coordinates do that or realize this by adding one extra dimension, and the transition between the Euclidean world and the homogeneous world and the other way around is just adding or removing this last dimension. If you add it, you add a 1 in there. If you remove it, you need to normalize it so that the homogeneous vector, so it becomes 1, the last dimension, and then you can actually drop the last dimension. And the key thing is, as a result of this, all the homogeneous elements are only defined up to scale. This holds for vectors, representing points, lines, but also for homogeneous matrices. They're only defined up to a scaling factor. Homogeneous coordinates can also be disadvantages in a few situations. So if you, for example, need to solve certain complex linear systems, as we will see it also later on in the course, for example, in bundle adjustment, then you have the effect that the scaling parameter adds a lot of potential unknowns to your equations, because you're increasing the number of unknowns because everything is only defined up to a scale factor. And in these situations, it can be suboptimal, and you may want to go back to Euclidean coordinates in those situations. There are very few, but sometimes it's worth going back to homogeneous coordinates because you have a smaller number of unknowns that you have, and especially for large systems, this can be advantageous. But the key thing you need to take into account in here is that homogeneous coordinates are a common tool that we are using in the remaining part of this course, or actually your whole study program. So make sure you're familiar with homogeneous coordinates whenever you work in robotics, computer vision, photogrammetry. you will need to know what homogeneous coordinates are and how to deal with them, what parameters are. If you want to read through a few things that I said, I recommend the book by Wolfgang Förstner and Wrobel on photogrammetric computer vision. We have a couple of books here also in the library, and they are these chapters 5.1 and 6.1 on homogeneous coordinates, points and lines, basically what I've presented here, on also transformations which you can study, you can rehearse this and even go deeper, because there actually is more information in there than what I have presented here. So with this, I thank you very much for your attention, and I hope I could stimulate your interest in homogeneous coordinates, and that you will study them at home and be able to use them on a daily basis, because they're really a very, very useful tool when you have to do a lot of transformations. So that's it. Thank you very much for your attention, and see you soon in the new courses. Thank you.